Okay, let's do Ohanian 5.77. This problem has a cable hung over an ideal pulley attached to the ceiling. But the difference between this problem and other similar problems we've seen is that this is not an ideal cable, it has mass. And in fact, you're given in the problem that the cable, which is perfectly flexible still, but has an overall length L, it has an overall mass M, and of course we know G, so those are the things we know. You're told that it's originally hanging with more rope on one side than the other, and that is given to you by X naught, the extra amount you've got on one side, compared to if it was equal on both sides. So we have a reference line here. So X naught is this distance, how much extra you've got on the right to begin with, and you have the same deficit here from an equal amount, where this would be L over 2 from there to there. So this is also X naught, but it's a deficit of rope. Okay, what you're asked for is, okay, starting from this condition, also starting from rest, V naught equals 0, question mark. What is the acceleration of the cable? And every part of the cable will have the same acceleration. And as a function of time, or as a function of distance, that's an important distinction. Time would be much harder. As a function of distance for how far this right end is below the equilibrium point. And also, what is the position? X, okay, for this cable. Now, this one is a function of time. Okay, so let's get started. And now you should, when you look at this problem, say, hey, this reminds me of something we've already solved, okay? The Atwood's machine, okay? Was just a couple of boxes, one on the right and one on the left. And again, we're asked for the acceleration and usually the tension in the rope, but that's not a question here. What's the acceleration of these masses as a function of time? And we've solved that problem. And our answer for this one was A equals mr minus ml divided by mr plus ml times g. And I can adapt that solution to this problem by realizing at any instant of time, we still have a mass on the right side and a mass on the left side, and the acceleration will be given by this formula. I don't have to redo it all. Although if you are tempted to, you could redo it from scratch with free body diagrams and Newton's laws, etc. Or you might just realize, oh, the overall net force on this 1D system is mr minus mlg. That has to be equal to the total mass mr plus ml times a. And so it's actually easy to get to this point just using ideas of this being a one-dimensional system and making the whole thing your system. Okay, and you could almost just write that down. But we don't have to, we already have it. So how do we apply it to our case? We need the mass on the right side and the mass on the left side at any given time or value of x. The mass on the left side will be equal to a couple ways of thinking about this, but you can say, well, what's the linear density? The overall mass times length of the entire string or rope, wire, is m over L. And you can multiply that by the amount or length of rope you've got on the right side at any instant. And that's just half the rope minus x, okay, on the left side, because if the rope is down here a distance x, remember x naught is the original position, but if it's down a distance x on this side from the equilibrium point, it's up a distance x on that side, so you have this much less rope. So this will be the equation for the amount of mass on the left side. I'm going to simplify it a little bit because these L's cancel, and just note that it's equal to 1/2 minus x over L, which is just a fraction of the rope, times the overall mass. Okay, now what's the mass on the right side? That is going to be similar. I could work it through in the step by step, but you might recognize that that just has to be equal to 1/2 plus x over L times m. Because the overall mass on the left and right side has to add up to the overall mass. And so when you add these two up, these terms will cancel, and you'll have 1/2 plus 1/2 is 1. Okay, so this will be the mass on the right side. Now we can just basically plug this into our Atwood's machine equation and write that the acceleration is the mass on the right, which is 1/2 plus x over L, minus the mass on the left, which is 1/2 minus x over L, divided by the total mass, which is the same terms but added instead of subtracted, plus x over L, plus 1/2 minus x over L, times g. We simplify this. These 1/2s cancel. Okay, but this minus times that minus is a plus, so we have 2x over L from this. When we look at these two terms, we say 1/2 plus 1/2 is 1, and these cancel. So just divide it by 1 times g, or 2x over L g. Done, actually. We have the first answer. What's the acceleration of the rope as a function of how far the leading edge is below the equilibrium point? Does it make sense? Well, if x equals 0, if the ropes are equal in length on both sides, we see the acceleration goes to 0, and that should make sense. Okay, good. So how do we proceed then to find x as a function of time, given this information? Well, let's stop and think for a moment. The acceleration, another way to express acceleration is the second derivative of position with respect to time. So this gets time involved, and we've just shown that this is equal to 2g over L x. Okay, so we have an equation that says the second derivative of x equals x itself times some constant, positive constant, and that you should recognize from your calculus class as a general solution of an exponential function with some constant out in front, which will have to end up giving us this. So x equals a, e, and if you take a derivative twice and get this in front, you'll have 2g over L times t. Because when you take the second derivative of this, you'll get the first derivative will give you square root of 2g over L. Another derivative will give you another factor of that, and multiply the square root times the square root, you'll just get this. So this is the general expression. Now A is determined by the initial conditions. So the initial conditions will actually determine A. What does initial conditions mean? Initial conditions is where did it start? X at t equals 0. Okay, well that we were told is x naught. That was given in the problem, and so we have the expression x at t equals 0 equals a, e to the 0, which will just be 1. And so this very easily tells us that this constant a in our general solution for the equation is just x naught that was given to us in the problem, up here, x naught. So our answer is x is a function of time equals x naught, e to the square root of g, 2g over L times time. And again, we see if time t equals 0, x equals x naught. As time goes on, x increases exponentially. So this falls faster and faster. And circle our answer, and we're done.